Hello everyone and welcome to this Solana for Ethereum developers course. So basically the course is for developers that are familiar with the Ethereum Virtual Machine and are planning on entering into the Solana ecosystem. They want to learn how to program in Solana. So let's dive right into it. The first thing I'm going to be explaining is the major difference between the EVM, that's the Ethereum Virtual Machine, and the SVM, which is called Solana Sealevel Virtual Machine. All right, so the first thing is that in the EVM or the Ethereum Virtual Machine, a contract account or a smart contract, when you deploy a smart contract, um, inside the smart contract, the code is stored. So the code, that's the executable file. You know, when you write your smart contract in something like Solidity, for instance, the code actually compiles down to bytecode, which the Ethereum virtual machine processes. So the code itself is stored in the contract account, and the storage is also stored. The storage, meaning if you're storing different variables, you can be storing an unsigned integer, a uint, you can store a string, you can store bytes, you can store a mapping. Everything is going to be stored within the contract itself. So meaning the program logic, that's the code, this code, the bytecode, and the storage are both stored in the contract. And that's very, very straightforward. That's what Ethereum developers understand up until now. But there's a little bit of difference with that when it comes to Solana. Everything in Solana is an account. Everything is an account. So a smart contract is in an account. The storage is in a separate account. Anything you want to do is in an account. Just put that in mind, first of all. So let's start with understanding what that means. First of all, in Solana, a smart contract, they are not typically called contracts in Solana, they are called programs. So on EVM, we call them smart contracts. On Solana, we call them programs. They are the same thing. On the Ethereum virtual machine, typically a contract has functions. So those functions are the different instructions that that smart contract can carry out. That's how it works in Ethereum ecosystem. But when we talk about Solana, instead of calling them functions, we call them instructions. So a program is made up of different instructions. A program is made up of different instructions, while in Ethereum, a smart contract is made up of different functions. They are the same idea basically. So now let's wrap our head around this account, the account model of Solana. So now don't forget that in Ethereum, we said that a smart contract contains the bytecode, right? It contains the bytecode and it also contains the storage. So meaning from the code, example in this place, we have a typical smart contract, just a simple storage. We have a variable called X, which can be set and can be gotten. So we can set it and we can also return it. This function can actually interact directly with the storage because they are both in the same place. The storage, this variable is stored in this smart contract, and this function is an instruction in this smart contract. So because they exist in the same context, this set function can refer to this global variable. But in the case of Solana, it doesn't happen that way. The way Solana is designed in a way in which the programs for the smart contracts are stateless, meaning they don't hold the state that the smart contract performs instructions on or performs functions on, if that makes sense. So what I'm trying to say is that in the case of Ethereum here, inside the same account, we have the same contract holds both the code, the executable bytecode, and the storage. These are the variables that exist within the smart contract. But in the case of Solana, imagine taking this out completely. So the storage, imagine the storage is kept in a separate smart contract, and the code is kept in a separate smart contract. There are some architectural patterns like that do that in Solidity for the sake of being upgradable, but we're not going to go into that. But just Ethereum developers are familiar with the fact that the storage exists in the contract address, inside the contract. When we come to Solana, we say everything exists as an account. They all have a field that is called data. Every account have a field that is called data. So for instance, this is an account, it has an address, and it has a field called data. This is an account. I'll come to what program derived addresses are in a second. But this is an account. They have a field called data. This is an account, this is an account, this is an account, this is an account. So what is inside the inner rectangle is the data. That's what I'm trying to depict here. So every account in Solana they have an address and they have a data associated with that address. So in the case of a smart contract, when you deploy a smart contract to the Solana Sealevel Virtual Machine, when you deploy a smart contract there, the bytecode, when the smart contract or the program, in the case of Solana, when the program is compiled, it compiles down to bytecode. So that bytecode is what is stored in the data column of that smart contract address, which is called a program in Solana. I'm sure that makes sense. So here in Solana, we have the data column of this program. Let's call them a program. Let's familiarize ourselves with the terms used in Solana. So we have a program account which has an address and it has a data field here. What happens when I want to store something in a program, as we usually do in smart contracts in Ethereum? How that happens is that we create a separate address. I know, yeah, it's a little bit weird when you first start with it. So what happens is that we create a different address, or we create a different account. Think of it in Ethereum as creating a separate contract. So when we create a different account, that account is what holds storage. It holds storage, individual storage. So for instance, this program can work with this storage. This is a variable. This is what a variable will be like in Solidity. This particular program derived address. This is what a variable will be. This is what another variable will be. So each variable is going to be stored in an address that is generated by that program or generated by that smart contract. Just think of it as, in Solidity, a contract can actually deploy another contract. So it's basically like one account is creating another account. That's how it happens in Solidity. So when a program creates an account for it to store data on, they are called program derived address, because the address is derived from the program and they are derived using seeds, or let's call them as inputs, that we can easily use to calculate the address of where this data is stored. You understand? So that it's not just lost somewhere on the chain and we can't find it, basically. So understanding this this account model of Solana is the key to easily transitioning between Ethereum and Solana. It is very, very, I'll say it's by far the biggest difference in transitioning from Ethereum to Solana. So let's come to code to our developers. So let's come to code and understand things a little bit better. So this is a simple contract in Solidity. We define the contract, simple storage. We initialize a variable called x, which is a uint. And we have some functions that can manipulate this variable that we stored. So the first function is function set. Of course, it takes in an input and it just sets x to that value. And we have get, which is public and is view, meaning it doesn't write code. It doesn't write changes to the blockchain. That's what view functions that mark view. Meaning it's just like basic Solidity and things like that. So it returns that variable. So imagine we have something like a separate contract might want to know what the value of X is. That contract can just call the get method, or a client, let's say our front end, we might want our front end to know what the value of X is. So we can just call the get method on it. So in this example contract 1, the architecture that it follows in Solidity or in an Ethereum virtual machine is similar to something like this. We have an address. This address is the address that the contract is deployed to. So meaning if you query this address on the blockchain, you're going to see that it's pointing to a contract. It is not an EOA. An EOA is an externally owned address. They're externally owned because they have private keys attached to them. So it's the private key that signs transactions on behalf of the account. But a contract, what tells the contract how to behave is the functions that we write in it. So for instance, this simple storage, we know that, when this contract is deployed, when we deploy the contract has some code. The bytecode has what the EVM understand. They are not zeros and ones, they are more of like opcodes, something like EVM codes, opcodes. Yeah. So instead of zeros and one that code traditionally compares to on like a normal machine, they compare to opcodes, which is these are opcodes, all these on the left. Compared to opcodes. So the opcode that this contract compares to is stored in code. And we also have the storage. Storage is what keeps the state of the contract. That's the data that is stored in the contract. So this is it here. The reason why I put this sample contract is to understand if this same contract was to be written on Solana. I talked about the Solana Sealevel Virtual Machine. I talked about the account model, in that everything is an account. So let's understand how we are going to rewrite this contract in Solana. So what happens when you deploy, let's say this smart contract is now written in Solana. In Solana, we write programs for smart contracts using Rust. They can also be written using C++ and C, but like by far the most popular one is Rust. So imagine we've written this contract in Rust in Solana. I don't want to write any Rust here because I'm just trying to explain the differences in the way the EVM and the SVM works. Let's just imagine that we've rewritten this contract in Rust. So now, what is the architecture that this contract is going to follow in Rust, right? In Solana, when we deploy a program, the program is deployed to an account, but the program is also compiled down to a bytecode. So when the program is compiled down to bytecode and you deploy it, it deploys to a Solana address. But instead of just being stored as code, that code is being stored in the data field of a Solana address. Every Solana address has a data field. Let me see if I can find it. So let's go to Solana account model. Yeah. So basically, everything in Solana is an account, and an account has different, let's call them attributes. So the attributes of an account, we have an attribute called data. So this data, when you are deploying a smart contract, what this data is going to hold is the bytecode of the smart contract you are deploying. Now, because that account is a smart contract, the executable parameter there, the boolean, is going to be set to true. Later on, we're going to come to Lamports and owner, but I don't want to dive into that right now. Don't forget, if the only thing that is stored in that new account that you generated, if the only thing that is stored there is the compiled version of, let's say this contract, is the compiled version of this contract. So I wrote a executable code, program bytecode, is stored in that data field. How about the variable X? When we want to read and write to the variable X, what is going to happen? Well, this is where Solana is different from Ethereum, in that to store this variable X on Solana, you need to create a separate account. Or rather than you creating a separate account, your program we need to create a separate account. And now this variable X is going to be stored in the data field of that account. Do you understand? So now let's come here. Let's say our program has generated a new account. The data field is going to hold the value of X, and the executable is going to be false because it is not a program. That account is not a program. That account is holding a data that's associated with a program. So the executable is going to be false, but the data is going to be whatsoever you want to store in this variable X. So in Solana, we have two accounts. For this smart contract to work properly, the first thing we deploy our smart contract to an account. The data field in that account is going to contain the executable bytecode. And when your program wants to read and write this variable X, this particular variable here, what your program is going to do is that your program is going to generate another account. That's where the idea of program derived address comes in. So your program is going to, let's say, is going to derive another address or derive another account, and is not going to store this X, this variable that it wants to read and write. It's going to store it in the data field of the account. I hope that makes sense. Believe me, if you can wrap your head around this concept, I'm going to put in this link in the description. By far, once you can wrap your head around this, I promise you, the transition is going to be so much easier. All right, so we have seen the architecture of this particular contract. So let's just take it a notch higher and look at a separate example contract. So this one, we're going to create the architecture together. This contract is just a little bit more complicated than the simple storage, but it's still a very, very basic contract. It's very easy to understand what's going on. So we have a contract, simple vaults, an address, which is the owner. And we see that here in the constructor, we're setting the owner variable to the message sender. And we have a mapping. We're mapping an address to a unit, and we're mapping it to balances because it's a vault contract. So, I mean, people deposit money and withdraw money. So we need a way to keep track of their addresses. So we have a constructor owner equals message sender, right? And we have a function deposit. So the deposit function is public, meaning it can be called from both within and outside the contract. So we have deposit function is payable, meaning ETH can be sent when calling this function. Basically, that's what the payable modifier means in Solidity. So what's happening here is that when someone sends money, we are storing that money, or we are storing that amount in the balances mapping. So we have the balances message of sender plus equals message of value. Message of value is like a global variable in Solidity that holds the value of Ether that is sent alongside the transaction. So we are storing that in balances. Balances, you can think of balances like an hash map, right? Or just think of it as a map. I mean, it's called a mapping. So it just maps a key value, maps a key to a value, a separate key to a separate value. That's what it does. So yeah, when someone calls the deposit function, it is updating the balances mapping. Then we also have the withdraw. We have the withdraw function. What the withdraw does is that balance equals, we reset the balance. Or no, we actually cache the balance of the user in a memory variable, or let's just call it a local variable. So then we set the user's balance to 0. And the reason why we're doing this is just because of there's something that's called CEI in Solidity, which is called checks, effect, and interaction. So we first make the effect that this function is going to have on this contract state. We first update it. We update the state before we now. Interaction is just like external calls, like when you're calling the function that is in a separate contract, or when you're sending ETH out, we do that last to prevent reentrancy attacks. We're sending the ETH that the user have put here before, we're sending it back to the user. So we're sending it to the message of sender, which is the call out function. And if it's not successful, basically we're going to revert, the function is going to revert to the withdraw error. And we also have a revoke ownership here. Actually, there's nothing this owner is doing. It's just for example purpose. So here we can revoke ownership. The user stop being the owner. We also have this special function in Solidity called receive. When the receive function is triggered is when you send ETH to the contract address. We've had a basic rundown of this contract. Now let's explain the architecture of this contract in EVM. And after that, we're going to explain the architecture of this contract in the Solana Sealevel Virtual Machine. All right, so let's say the contract is deployed to this address. First of all, we're going to have, like we saw here, so we're going to have the bytecode. Let's make the code a little bit more because, the contract is a little bigger than this. So we say that in the contract, the code is stored, and we also have these variables. We have an address called owner, and, for a little bit of advanced Solidity developers, we know that Solidity stores variable in slots. So this one is going to be in slot 0, and mapping will actually not be in slot 1, right? Because normally we're meant to have 0, 1, 2, 3, then we'll continue like that. But mapping is not going to be in slot 1 because we don't know all the elements that is going to be in a mapping. So we can't put it in between. When we understand the way a mapping is stored in Solidity, we can easily wrap our head around the program derived address concept of Solana. Yeah, so this contract has been deployed. The bytecode is on chain. Owner is actually stored in slot 0 within the Solidity, within this particular contract. Let's not look into how mapping works yet, but let's just say the mapping is calculated arbitrarily. Let's just say address 0 is going to be balance of address. We know that this contract address, when deployed, is going to have the bytecode and is also going to have the storage, the state of this smart contract. Let's see how that's going to be different for the Solana Virtual Machine. So the first thing is that this contract is going to be compiled, and when it's compiled, it's going to be deployed. But don't forget, in Solana, everything is an account. So it's going to be deployed to an account, and then the bytecode is going to be stored in the data field of that account is deployed to. You understand? And because it's a program, the executable field of that account is going to be true. I hope that's clear. How about the state that the smart contract is going to manage? The variables that are contained within the smart contract. So we have the owner and we also have the balances. So the way it works similar to this. This is the owner variable slash state. So variable state. When you are executing this code and you want to communicate with the owner, this program account creates a new account. So it creates this account, this particular account, then put an arrow. So this code creates this owner variable. So we see that when we want to interact with the owner variable, this program creates a new account. Now, when it creates a new account, it stores the owner. So when we have the data, let's just call this struct. Let's just call this state 1. State 1. And it stores the owner. It stores the owner in the data field. It stores the owner in the data field of that address or of that account that it generates. All accounts, basically, they have the same fields. So we also know that this account is going to have an executable, field. But because this is not a program, it is just there because a program created it to store data. So the executable is going to be set to false. This account that this program created is called a program derived account. A program derived account. So that's how an account stores its states in Solana. It creates new account and stores what it wants to store in the data field of the account. All right. So we've got over the owner variable. Now let's get over the balances. So the balances is key and value. Where I store the balance of an address will be different from where I store the balance of another address. So because they are numerous like that, this program can create as many accounts as it needs to store its state, basically. So let's do that. So instead of this being owner, it's going to be balances address 0. And let's just call it states. Balance address 0 state. So it creates an account. Obviously the account is going to be different. The account ID is going to be different. So it stores data. Instead of data, let's call it state 2, and it's not going to be an owner. Let's call it balance. So now imagine I execute I call deposit function. This deposit, imagine I call this deposit function from this my address. So what's going to happen is that this program is going to create a separate account for me to hold the balance of that address that I just called. So it's holding the state of a separate address. So when a separate address deposits money and it wants to store that state, the structure is still going to be identical to state 2 because it's storing the same thing, and it's going to have the balance value. That's going to be the value that this address sent alongside the transaction. The executable is going to be false, of course, but we can see here that it created another account. So you get the point now. If a separate address calls this function, it's going to create a separate programmed derived address. It's going to create it. It's going to create it. But the thing is that this program knows the way it generates all this address. So imagine this account deposits more money. Don't forget here that we have the deposit function. It does plus equals method of value. It does plus equals what was there before. So imagine I already had a balance here, and this same account, this particular account, this my account calls that function instruction. In Solana, it's called an instruction. In Solidity, we can call it a function. So it calls that instruction again. What's going to happen is that this program is going to generate this address ID, but it's going to see that it exists already. And seeing that it exists already, it's going to read the state. When it reads the state, it's going to update this value. So let's just call that value plus plus. So that's the updated version of this value. So basically, this is the account model of Solana. In Solidity, everything is stored within the contract itself. But in Solana, the program bytecode is stored in an address, but when it needs to create state, it generates more accounts, generates more accounts, generates more accounts, and it manages them, it updates them accordingly. And it can even delete them actually. Because in Solidity, you can also delete a variable, you delete keyword, you can remove it off chain, or reset it back to 0. And in Solana, that's also possible. So we can also terminate addresses. So I put this mapping here I put it for a purpose. The uint 256, or the value of every separate address in this balance, has to be stored in different slots. And the way it knows the slot that is stored is because it calculates it, right? Solidity, or the EVM, calculates the EVM actually. The EVM calculates the location of this storage, of every separate address. It calculates their storage slot. It calculates it internally. And the way it does that is this. So when we come here, you see that mappings and dynamic arrays, due to the unpredictable size, mappings and dynamically sized array types cannot be stored in between the state variables. So you see what I did here. That one is stored in slot 0, the next one is slot 1. If it could be stored in between, this is meant to take slot 1, and this mean amount is meant to be slot 2. But that's not the way it works. So you say it can be stored in between state variables and following. Instead, they are considered to occupy only 32 bytes with regards to the rule above. The rule above is just talking about slots, and then without understanding, we know that mean amount will still be stored in index 2. 0, this will take index 1, this will take index 2. The balances is going to keep index 1, but it's not going to store the mapping in index 1. It's just going to take up index 1 space. It's not going to store the balances mapping in index 1. So we know that mean amount is going to go to OX2. So I just updated that due to this new knowledge that we have. And the elements they contain are stored starting at a different storage slot that is computed using a KCAC 256 hash, right? So let's look at mapping. Okay, the value corresponding to a mapping key is located at KCAC 256 HK.P, where dot is concatenating. So basically, we're fusing this together, and H is a function that is applied to the key depending on types. So for value type, H passes the value to 32 bytes. We know the EVM is actually a 32-byte machine, so it stores everything actually as a 32 bytes value because it's a 32-byte machine. So it pads it in 32 bytes, the same way storing the value in memory for strings and byte array HK. Right. I don't want to delve deep into this, but it's not very, very difficult. It just applies an hash. It applies an hash to the storage slot. So we know that this mapping takes up storage, is declared to be in storage slot 2. So it takes up the storage slot. Sorry, this index 1, but it's slot 2. Sorry. I mean, this is just the way it works practically. But don't forget slot OX2 is actually this slot 3, but the name of the slot, because it's zero-based index, so the name of the slot is going to be OX02. So we know that balances takes up the second slot. So what it just does is that for me to calculate the location of where address 0 will be stored. Let's say address 0 is a proper address and it wants to store its value in these balances. What it does is that we take in the KCAC 256, right? So it's something like this, similar to this. KCAC 256. We take in the storage slot. And we take in the address. That's going to the address 0. And we hash it together. This is going to give a 32-byte value. And that 32-byte value is the slot that we're going to store this value. I'm not exactly sure that this is the pattern, but it's very, very similar to this. And I don't want to go so much in depth. But basically what I'm trying to bring out is that to calculate where a mapping is stored, Solidity has a way in which for the same exact address, it can generate that same slot. So if this same address 0, calls this function again and it wants to update the balances, Solidity is going to generate a storage slot that is going to correspond to where the balance value of that address was stored before. Oh my god. I hope you understand. If you don't understand, just go back and listen to it a little bit again. Oh, I'm also going to link this in the description below. So basically what I'm trying to say is that there is a pattern in which it can calculate the storage slot. So that's the same thing with program derived address. This program account, when it's creating different addresses to store its state, it has a pattern that it uses. So that anytime this address comes to modify the state, it can generate the same account ID or address. It can generate the same address and update it just the same way a Solidity mapping dynamically generates the slots for a particular key. I think you understand. Yeah, alright. I need to go and drink a little bit of water right now. My throat is getting dry. Let me see if I can create a public link. I'm going to link this page in the description. Alright guys, I'm going to see you in the next tutorial where we are actually going to start writing some Rust code. What we're going to do is that we're going to take this example that we've written here, and we're going to take this example that we've written here, and we're going to write it in Rust. Alright, thank you for watching. I'll see you in the next video. Bye.